Welcome to AI Paper Slop. Today, we are jumping straight into a paper called Next Generation Agentic Reinforcement Learning Systems Enable Self-Evolving Agents.
Quite a title.
Yeah, right? It's by Ran Yan, Wei Fu, and a team from Ant Group, HKUST, and Tsinghua University. And you can grab the code over at github.com, Ariel Brave Project Ariel.
Definitely worth starring that repo.
Oh, absolutely. So here's the core insight right out of the gate. We're deploying LLM agents constantly right now at a massive scale.
Right, everywhere.
But they're fundamentally static. The second you deploy them, their weights, their prompts, the toolkits, they're completely frozen.
Yeah, totally frozen in time.
Exactly. And the authors argue that the bottleneck holding us back from, enterprise scale, continuously self-evolving agents, it's actually not a lack of better RL algorithms.
No, it's an infrastructure problem.
Yes. The real missing piece is an agentic online RL system. So to fix this, they propose an architecture with basically 3 co-design pillars.
Which are super interesting.
Yeah, they've got a standardized trajectory data protocol, an enterprise-grade data proxy, and a unified evolution control plane. And they actually built a working prototype called Ariel 2.0 to prove it works.
Which is huge, because if you're an ML engineer tuning in, you know the absolute dread of the current manual improvement loop.
Oh man, the pager goes off.
Exactly. An agent fails in production, your pager goes off, and what do? You export the logs, you're sitting there manually combing through traces trying to guess what the model was even thinking.
It's just staring at JSON files.
Right. And then you have to curate a new data set, kick off some offline fine-tuning job, basically rewrite the whole agentic loop, and just pray it actually works when you redeploy.
It's a complete nightmare.
It's disjointed, tedious. I mean, we do have examples of personal self-evolving agents.
Like OpenClaw?
Yeah, exactly. Systems like OpenClaw that learn from local user interactions. But taking that to an enterprise scale is just a totally different beast.
Because of the compliance stuff.
Compliance, multiple tenants, strict data boundaries, vastly different asynchronous tasks. You can't just, throw standard preference optimization at it.
Like PPO or DPO.
Right. You can't just throw that at a massive, unstructured pile of production logs and expect the agent to safely fix itself. You really need an architecture that systematically captures and processes these failures in real time.
Okay, let's unpack this. Because to fix a mistake, the system first needs to understand the actual anatomy of that mistake,
Exactly.
right? And standard observability logs, they just aren't cutting it for agentic workflows. Think about standard telemetry today.
It's pretty basic.
Yeah, you get the prompt text, the latency, maybe token counts, and, a final HTTP error code.
Yeah, basically nothing about the reasoning.
Right. It's essentially a restaurant receipt.
Yeah.
Tells you what you bought, how much it cost, what time you left. Great for auditing the bill, but not much else.
Yeah. It doesn't tell you how the food was cooked.
Exactly. So the authors propose this Agent Trajectory Data Protocol, or ATDP. An ATDP is less like a receipt and more like having, a 4K camera positioned right over the chef's shoulder in the kitchen.
I like that analogy.
Yeah, it's specifically designed to let you trace a bad meal back to the exact second the chef decided to use, like salt instead of sugar.
Right, which gets to the heart of credit assignment.
Exactly. You aren't just firing the chef because the meal was bad. You're fixing the specific step where the recipe failed. But I have to challenge this premise just a little bit from an infrastructure side.
Oh, the storage costs.
Yeah, storing a token count is cheap. But storing every single thought process, every scratchpad entry, the whole intermediate context window for a high-throughput enterprise agent.
It sounds awful.
It sounds like a total storage nightmare. Do we really need to log the entire cognitive process of the model for every single API call?
Well, what's fascinating here is that the paper tackles that exact operational concern. They have this principle they call decision-relevant bounded revelation.
Decision-relevant bounded revelation. That is a mouthful.
It is, but the idea is actually super elegant. The system doesn't need unrestricted disclosure of every single hidden token.
So no multi-gigabyte chain of thought dumps.
Right, no massive dumps. You just need enough structural data to support that step-level RL credit assignment we were talking about.
Okay.
Like, when a multi-turn agent fails on step 7, you need to know, was the failure caused by the observation it got at step 2? Or was it a faulty prompt fragment at step 4?
Or just a totally hallucinated tool call at step 6.
Exactly.
So how does the schema actually map that out? How do you standardize a thought process across different agents?
Basically by heavily enriching this standard Markov decision process abstraction.
Oh, okay. Let's get nerdy.
Yeah, so the ATDP schema formally defines an intermediate step using a specific set of variables. First, you have odd, which is the observable status.
With tool outputs or what the user said.
Right. Yep. Then you have HT, the hidden internal status. This is the crucial part. It captures the agent's scratch pad or its reasoning summary at that exact moment.
Right.
Then there's at, the chosen action. Think of a tool call with typed arguments. Following that is UAC Barema, the action outcome.
Okay, making sense so far.
Then IT, the reward signal. And finally, you have MT, which is the metadata.
For governance stuff.
Exactly. Model version, tenant ID, cost, safety status, all that critical compliance metadata.
Okay, I want to pause on that reward signal. The right. Because in a textbook RL environment, like playing chess or a basic simulator, the agent takes an action and boom, the environment instantly returns a reward.
Right. It's perfectly synchronous.
But in a deployed enterprise setting, rewards are basically never immediate.
Almost never, yeah.
Like, if an agent writes a piece of code for a PR, the feedback might be a human developer leaving a comment, like 3 days later.
Yeah, or a ticket reopening a week later.
Exactly. So how does the protocol handle a reward that shows up on a Tuesday for an action taken on a Saturday?
It's tricky.
Because you can't completely overwrite the context of everything that happened in between, right? The agent might have had 3 new system prompts deployed since Saturday.
Right, and that is a massive challenge for online RL. The paper actually formally defines this as late-bound learning signals.
Late-bound learning signals, okay.
Yeah, because if you just update the live database record 3 days later without being careful, you risk totally losing the exact environmental state that existed when the decision was actually made.
Which ruins the training data.
Completely ruins it. So ATDP solves this by treating delayed feedback as a first-class property of the data stream. They use something called retroactive augmentation.
So it appends it after the fact.
Exactly. It appends the delayed reward to the original event record, but it strictly preserves the versioned provenance.
Oh, that's smart.
Yeah, so the training system knows exactly what the environment looked like, what the tool schema was, and critically, which exact model checkpoint was running at the exact millisecond the agent made the decision.
Regardless of when the reward actually arrives.
Exactly.
Okay, so we have this highly enriched, perfectly structured ATDP schema on paper.
Sounds great on paper.
Right, but in reality, if you look at a modern enterprise, you are looking at a total spaghetti code landscape of different frameworks.
Oh, 100%.
Like one product team is using LangChain, another is on LangGraph or Crew AI.
Someone's writing raw Python scripts against the OpenAI SDK.
Yes, or experimenting with the new model context protocol. You cannot ask all these product teams to halt development and rewrite their entire architecture just to output this new ATDP schema.
No, they would laugh you out of the room.
Totally.
Yeah.
So how do we actually extract this trajectory data without breaking production?
Well, that is where the second pillar comes in, which is the enterprise-grade data proxy.
Okay, the proxy.
Yeah. It's designed to sit right in the middle of this heterogeneous ecosystem. It basically intercepts traffic at stable execution boundaries.
Meaning it sits between the agent and the LLM.
Exactly. It acts as a transparent intermediary between the agent and the inference engines, the agent and its tools, and even the agent and its memory retrieval systems.
So it's essentially a man in the middle for the agent's API calls.
Pretty much, yeah.
Are we talking about wrapping the client SDKs here, or is this happening more at the network layer?
It's typically at the network layer or via a lightweight standardized API gateway that basically mimics the endpoints the agent already expects to talk to.
So the agent has no idea it's being intercepted.
None at all. The agent sends what it thinks is a totally standard LLM API request. The proxy intercepts that payload and then losslessly serializes the multi-turn interactions into those structured ATDT streams we just talked about.
And then just forwards it to the actual LLM.
Yeah. The framework running the agent is completely oblivious. And while it's doing this interception, it's also handling what the authors call reward harvesting.
Which is such a brilliant concept.
It really is.
Because the proxy is actively looking for operational state changes and turning them into candidate learning signals, right? It's not just waiting for explicit, 5-star user ratings.
Right, because users never leave those ratings anyway.
Exactly. If a customer support agent resolves a ticket, but the proxy sees that the user reopened it an hour later with a really frustrated comment.
That operational state change is harvested immediately.
Yeah, as a negative reward signal for that specific trajectory.
But, and this is super important, we have to remember that not all signals are safe to optimize against directly.
Oh, right. Safety and governance.
Yeah, which brings us to a really critical technical insight about the proxy. It's not just an observability tool. It is literally the first operational safety boundary of the RL loop.
Meaning it stops bad data from getting into the training set.
Exactly. Before any of this trajectory data hits a training queue, the proxy enforces cross-tenant aggregation with strict isolation.
So tenant A's data doesn't train tenant B's agent.
Exactly. And it applies data classification rules, so it's redacting sensitive customer PII, personally identifiable information, before the learning even happens.
It enforces governance at the interception layer.
Right, rather than trying to scrub the data after it's already, poisoned the training pipeline.
That makes a ton of sense.
Right.
I want to drill into a phrase the authors use heavily in this section, though. They talk a lot about replay capability.
Oh, yeah. This is huge.
They draw a really hard line between simple monitoring and actual replay. Why is that distinction so crucial for actually training the agent?
Because a learning system has to answer counterfactual questions.
Counterfactuals.
Yeah. Monitoring just tells you what happened. It says, hey, the agent called the billing API, and the API returned a 404 error.
Right. Just a historical fact.
Exactly. But to train an agent via reinforcement learning, the system needs to be able to ask, would the agent have successfully resolved the ticket if it had been given a slightly different system prompt?
Or if the tool schema had better descriptions.
Right. And to answer that, you have to be able to replay the exact scenario offline.
But you can't always do that safely.
Right.
Like if the agent's action was to send a real email to a customer or, I don't know, drop a database table.
Please don't drop the table.
Right. You can't just replay that during an RL training loop and spam the customer 100 times while the model learns.
No, absolutely not, which is precisely why the proxy categorizes events. The system differentiates between deterministic replay,
Like a math calculation.
yeah, math, or an isolated sandbox execution. It differentiates that from approximate replay. For actions with external side effects, like sending an email, the system relies on mocked responses or historical caches to approximate the environment.
Oh, gotcha. And what if you can't mock it?
If an event is entirely non-replayable and can't be safely mocked, the proxy just flags it. Because if you can't accurately replay a trajectory, it is fundamentally untrustworthy for sequential training data.
So the proxy basically acts as a bouncer, ensuring the data feeding the RL loop is valid and safe. Okay, so we've perfectly captured the mistakes with ATDP. We've safely extracted them from production using the data proxy, and we've verified they can be replayed.
Yep, the data is ready.
Now we hit the actual decision-making engine. Here's where it gets really interesting. Who, or what, decides how to actually change the agent's behavior to fix the problem?
Well, that falls to the third pillar, which is the Unified Agent Evolution Control Plane.
The control plane.
Yeah, and this is where we have to basically fundamentally shift how we define an agent. The paper really stresses this. A deployed agent is not just a neural network. It is a composite policy.
A composite policy. Let's unpack that for a second, because I feel like we constantly conflate the LLM with the agent itself.
All the time. People use them interchangeably.
Right, but the model is really just the reasoning engine.
Exactly.
The actual deployed agent is the base LLM, plus the carefully crafted in-context harness, plus the vector database for memory retrieval, the available tools, the hard-coded guardrails. It's a huge composite package.
Right. And if we connect this to the bigger picture of self-evolution, it means we shouldn't just reach for the heaviest tool in the shed every single time something breaks.
Meaning, don't just retrain the model weights for every little bug.
Exactly. Blindly running post-training RL to update model weights every time an agent makes a mistake is like a massive sledgehammer for what might be a very tiny nail.
And it's super expensive computationally.
Super expensive, and you risk catastrophic forgetting. So the control plane introduces this concept of multi-surface adaptation.
Okay, multi-surface adaptation.
It basically treats self-evolution as an automated, governed decision problem.
Yeah.
It looks at the failure mode and matches it to the most efficient intervention surface.
Okay, give me a concrete example of how it chooses between those surfaces. Because in a traditional setup today, an engineer just looks at a Grafana dashboard, guesses the problem, and maybe goes in and tweaks the prompt manually.
Right, a lot of trial and error.
So how does the control plane make that choice dynamically?
It looks at the clustering of the failures. So if the agent's trajectories show it keeps missing specific factual context, say, about a newly updated company policy.
The control plane knows it's just missing knowledge.
Right. So it triggers a memory insertion. It just updates the retrieval context. That is the absolute cheapest, safest fix.
That makes total sense.
But alternatively, let's say the failure clustering shows the agent has the right facts, but it keeps routing to the wrong tool, or it consistently messes up the JSON formatting for a specific API call.
Then memory won't fix it.
Exactly. In that case, the control plane triggers an automated edit to the in-context harness, or it actually rewrites the tool schema descriptions so they're clearer for the model.
Wow, so it modifies its own prompt.
Yeah.
But what if the failures are, like, really broad? What if the agent is failing across multiple tenants, across entirely different tasks, and tweaking the prompt or the memory just doesn't move the needle at all?
See, that is when the control plane determines that the problem is fundamental to the model's core reasoning capabilities.
Oh, so it escalates it.
Yes. That broad failure pattern justifies triggering a full model weight update via online RL.
And what's wild to me is that this isn't some ML engineer sitting at a dashboard making these calls. The control plane is triggering these interventions totally automatically.
Yep. It's completely automated.
It's just constantly reading trajectory statistics like remote evaluator scores, user correction rates, canary deltas, and just acting on them.
It is, but it acts with strict safety and governance. I mean, automatic triggering doesn't mean unreviewed, chaotic, hot swapping of agent behavior in the middle of production.
Oh, thank God. That sounds terrifying.
Yeah, that would be bad. The control plane enforces what the authors call replay first evaluation.
So it tests the fix first.
Exactly. If the system decides to update a prompt harness or train new model weights, that new composite policy must pass offline regression tests before it ever sees live traffic.
Oh, nice.
It is tested against the replayed trajectories of past failures to ensure the update actually fixed the specific problem. And critically, it's tested against a golden data set of known successes, just to ensure the update didn't break anything else.
So version rollback is basically a first-class citizen here.
Oh, absolutely mandatory.
If the newly evolved agent somehow degrades performance in production, the control plane just immediately rolls it back to the previous composite state.
Right, because an agent that can't explain what changed or be reverted, that isn't self-evolving, it's just drifting.
Just drifting. Wow. The control plane basically brings rigorous systems engineering and MLOps directly into the RL loop.
That's exactly what it does.
So the theory is beautiful, but the rubber really has to meet the road eventually. If you're an engineer listening to this, you really want to know what this looks like when you deploy it into a real tech stack.
Yeah, how does it actually work in practice?
Right. So section 4 of the paper details the working prototype they built, which is Ariel 2.0.
Yeah.
And to keep the scope manageable, the authors didn't build every single evolution path. They really focused primarily on the hardest one-on-line policy LLM weight updates derived directly from deployed trajectories.
And the architecture of Ariel 2.0 is remarkably elegant, mostly because it abstracts the immense complexity of RL entirely away from the application layer.
So the proc teams don't have to deal with it.
Exactly. They took an existing offline RL framework, the original Ariel system, and reorganized it into this agent service-oriented online RL loop. So they exposed the heavy RL infrastructure, like the rollout workers and the training actors, as a back-end microservice.
Okay.
The system basically relies on 4 main components: an inference gateway, a router, the data proxy we analyzed earlier, and agent compute workers.
And those agent compute workers wrap standard inference engines, right, like VLLM or SGLang.
Yep, right alongside the training actors.
Yeah. Okay, so what does this all mean? Let's trace a request to make this really tangible. Say you have a custom customer support agent. The paper uses the Hermes agent as an example.
Right, the Hermes agent.
So it's currently running in production. To hook this up, the brilliant part is that you do not touch your Hermes agent's workflow.
You don't rewrite a single line of agent code.
You leave the planning module alone, the memory integration alone. All you do is go into your deployment config, take your standard local LLM inference URL, like, say you're pointing it at a local VLLM server, and you just replace it with the Ariel 2.0 inference gateway URL.
The integration cost is virtually zero. It's amazing.
Yeah. The Hermes agent just continues to issue what it thinks are standard multi-turn API requests. It is completely unaware that the backend is shifted entirely.
Exactly. So the Ariel 2.0 gateway normalizes those incoming requests and then passes them to the router. And the router is absolutely critical here because agent workflows are deeply stateful.
Right. They have multi-step context.
Exactly. If an agent is in turn 5 of debugging a complex user issue, you cannot have turn 6 suddenly bounce to a different, disconnected proxy instance.
Because it would lose the whole conversation history.
Right. So the router maintains strict session affinity. It locks that specific task trajectory to a specific data proxy.
Okay, so the data proxy intercepts that multi-turn tool-using stream. It records the ATDP trajectories flawlessly, and then passes the request to the agent compute worker to generate the actual text response.
Yep.
But because it has perfectly captured that interaction, complete with those delayed rewards we talked about earlier, it feeds that data directly into the online RL training loop.
It completely closes the loop. The data generated by the deployed agent's native workflow becomes the exact training data used to optimize its policy weights, and it's all dynamically allocated behind that microservice interface.
That is just so clean.
It really is. It eliminates the gap between offline post-training environments and real-world deployed agent behavior. Like, you aren't trying to build a synthetic sandbox that mimics production anymore.
You're just learning directly from production.
Continuously and safely.
It is a massive paradigm shift.
Yeah.
And it really brings us to the big takeaway of this deep dive. Building better, more capable agents is shifting from being purely an algorithmic challenge.
Where we're all just hunting for a slightly more efficient PPO variant.
Right. It's shifting from that to a hardcore systems engineering challenge. If we want agents that continuously improve in the wild, we can't just throw raw compute at them anymore.
No, we have to build the foundational infrastructure.
The protocols, the proxies, the control planes, all the stuff that allows them to learn safely and systematically from live traffic.
We really are transitioning from building static models to building governed learning substrates. But before we wrap, I do want to leave you with a final, somewhat provocative implication of this paper.
Ooh, all right. Let's hear it.
It's something that goes beyond the immediate engineering benefits and touches on the reality of operating these systems at scale. I mean, if we successfully build this control plane and we deploy it across a huge enterprise, we are essentially creating a reality where agents are automatically and continuously rewriting their own operational rules.
Right, based on live traffic.
Exactly. They are inserting new knowledge into their memory, they're tweaking their in-context harnesses, and they're modifying their own tool schemas potentially thousands of times a day.
Just an endless automated loop of micro-adaptations, which is incredible for performance, but absolutely terrifying for observability.
Right.
Because the logical endpoint of that is a system that evolves entirely beyond our comprehension.
That is the exact paradox we are heading toward. I mean, think about it. How long before an enterprise agent's composite policy becomes entirely unintelligible to the original human developer who deployed it? You deploy an agent on a Monday with a clear, logical, human-readable set of instructions and a predictable tool set. But a year later, after millions of automated micro-adaptations and weight updates, that agent might still be resolving support tickets with 99% accuracy.
But its internal prompt structure, its tool writing logic, the memory retrieval patterns, they might look completely alien to us.
Completely alien. We might solve the static agent problem only to wake up and realize we've engineered a highly optimized black box that works perfectly, but that literally no human engineer can actually debug or conceptually understand anymore.
You fix the evolutionary bottleneck, but you completely lose the map of how the agent actually thinks.
Exactly.
Man, that is an incredible technical achievement, but with massive MLOps implications that we are clearly only just beginning to grapple with.
For sure.
Well, if you want to dive into the technical specs, explore the full ATDP schema variables, or see how you might route your own agent trajectories through this proxy, you absolutely have to check out the paper and the GitHub repository at github.com for your just Project Ariel. Thanks for joining us on this deep dive into AI paper slop, and we'll catch you next time.